Health technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job? To redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I'm pleased to have with me in the studio Dr. Ann Fisher, a program manager since 2017 in the agency's Defense Sciences Office. That's where she and her fellow program managers, PMs as they are known in-house, forage deeply into the fundamentals of chemistry, physics, optics, materials, and other disciplines in search of new scientific and engineering foundations for technologies that can matter for national security. Ann is making her mark at DARPA as one of the few chemists in the agency. After receiving her PhD in chemistry from Michigan State University with a catalyst project that relied on electrically conductive diamond, she did a couple of research stints at the Naval Research Laboratory, which is the Navy's broad-based corporate laboratory. She also got her feet wet in the science and technology policy world as a fellow at the American Association for the Advancement of Science, publisher of Science magazine. Then, in 2009, she began what continues to be her partnership with DARPA, first as a contract scientist and since early last year as a DARPA program manager. One of her prized accomplishments, inspired by her own successful journey to become a woman scientist in a male-dominated profession, she created a Girl Scout chemistry interest patch with the goal of getting more girls interested in the molecular wonders of the world. Dr. Ann Fisher, welcome to the studio.
It's great to be here. Thank you.
So before we talk about your sizable portfolio of DARPA programs with names like Make It and Molecular Informatics and this one, Spectral Combs from Ultraviolet to Terahertz, you've got to tell me how your interest in chemistry arose. Because as you well know, most people, men or women, bolt with panic the instant you say something like the periodic table of chemical elements.
Yeah, so that actually goes back to elementary school. Sitting down at the kitchen table in my house growing up, and my parents bought a chemistry set, that things I don't think you could probably buy today. They wouldn't be in the store today. It literally had a rack on it with all sorts of different chemicals.
Very dangerous chemicals.
Dangerous chemicals that I probably don't even want to know what they were. And it had experiments. And from an early age, my mom specifically, my parents both sort of just encouraged this sort of exploratory, experimental nature, and I just latched on to chemistry. Then through high school, it was sort of all over sciences I couldn't really choose, and it was really solidified in my undergraduate education at the College of Worcester in Worcester, Ohio. There was something about chemistry and the way it was taught in that department that really just kind of catalyzed essentially the rest then of the graduate career and postdoctoral work.
Tell me just a little bit about that dissertation project where you used electrically conductive diamond.
Right. So the group I was in at Michigan State was really focused on developing electrically conducting diamond electrodes for a variety of applications. And I was in the section of the lab that was working on power and energy applications. So we were actually trying to develop new and ultra-stable materials for fuel cells. That really was both a project related to my love of chemistry, but with a very practical application. And that was in, the early 2000s, where there was a lot of work on fuel cell development and a lot of work on sort of alternative energy that continues today. But that was really the genesis of what we were doing there. And then fuel cells
being technology that actually relies on fuels, even something like hydrogen, but maybe hydrocarbons, and produces from that electricity.
That's right. And one of the problems at the time was the stability of the electrodes themselves. And electrodes are what convert sort of the fuel, if you will, the hydrogen in an example case to electrons, to electricity. And we were trying to enhance the stability of those materials.
Okay, and then before we move on to your stints at Naval Research Laboratory, I do just want to confirm that you did not walk with any of those diamond electrodes. You left them?
I left them, unfortunately. They're not as beautiful as you might imagine. They're these thin films of really sort of gray.
Okay, so
materials.
they're more utilitarian.
Yeah, absolutely.
Useful. You don't wear them. So tell me about Naval Research Lab. The reason I want to know a little bit about that is because I actually worked for NRL for a while. I was hired to write a institutional history for their 75th anniversary, so I'd gotten to know the place pretty
cool.
well,
Yeah.
and it intrigued me to see that you had worked there.
Yeah, so I worked there. I came right out of graduate school to a postdoc at Naval Research Lab, working with Deborah Wallison and Jeff Long. And they worked on power and energy related applications, not with diamond, but with other electrode types. And so I was essentially taking my interest in sort of power and energy and alternative energy sources to a group that had a long history of success in that space. So I spent about 2 years there working with them.
Yeah, actually, I'd gotten to know Deborah when I was there at the time.
Oh, excellent.
So that's very exciting for me to hear. And then a funny thing also is I worked at AAAS as well, the American Association for the Advancement of Science, where you've learned a thing or two about science and technology policy. So that's an interesting shift in a way from the lab and into this other component of the whole science enterprise.
Yeah, so I actually learned about the AAAS fellowship when I was in graduate school. And it's a 1 year, potentially a 2 year program if you renew for a second year, where scientists and engineers come to D.C. and either serve on Capitol Hill and work for members of Congress or a congressional committee, or work in the executive branch. And so I spent my time as a AAAS fellow working at the National Science Foundation, and that was my first kind of entry, if you will, into policy by the purse strings. Essentially, how do we sort of change the scientific endeavors by funding specific areas for technology development?
Okay, so I'm also realizing there is something weird about, I guess, both of our CVs, because I'm swerving you now into your DARPA experience, and I've got DARPA on my resume as well. I think this is it. I'm not going to mention it again, but there are some parallel. I
looked you up and just followed you wherever you went.
So let us turn to your DARPA experience. You started as a CETA contract worker, and then you became a program manager in the Defense Sciences Office. So talk about the early CETA phase, and then how that kind of segued into your program manager phase.
Yeah, so that's a really interesting thread, because it shapes what my interests are today, all the way back to the first day that I worked at DARPA. So I actually heard about DARPA from a friend who worked for a company that had a CETA contract here. And while he didn't work at DARPA, he said, "Hey, there's this opportunity. Is this something you'd be interested in?" This was right after my AAAS fellowship was winding up. And I said, that sounds pretty interesting. And the opportunity was working with a mathematician in the Defense Sciences Office, Ben Mann. And Ben is sort of a genius mathematician who wanted to surround himself by people who knew other things, chemistry, biology, physics, those sorts of things. And so he was really looking for someone to come in to provide a lens to chemistry that sort of he could then think about how to apply mathematics in that space. And it was probably one of the scariest first days of my life, but I decided to do it anyway. It was an amazing opportunity. And really the sort of the math and the programs that he had going still, again, as I mentioned, sort of impact my thought process today. I mean, the programs I have today have AI components, machine learning-based components, complexity, those sorts of things, which are things that sort of he had addressed from a fundamental level many years ago when I started. And it sort of weaved through, as DARPA goes, none of us are here for all that long. And so worked for a material scientist and a chemist, sort of getting back a little bit closer to my roots, but still being able to bring in those things that I learned from Ben and from his performers and the programs that he had and was developing.
Right, and just for listeners who might not know how the sort of the basic structure here works, there's a program manager who is in charge of a portfolio of programs, and we're going to talk about that in your case soon. But then each program manager has one or several CETAs who assist. And so what might be a typical role for a CETA on a typical program? I mean, say when it comes to working with those research groups that become part of the overall program effort?
Yeah, so it really depends on the program itself and the program manager. But generally speaking, you can serve as a subject matter expert, where you're the person in the room with that expertise in chemistry. And when questions arise about, for example, how to apply mathematics to a chemistry-related question, you can then think about, well, if I think about a material and I think about some structural considerations of that material, those have dimensions associated with them. How then could that be addressed by a mathematical design for material of interest? So it's providing that subject matter expertise, but then also how do you bring that perspective of that field into the program at hand? Because it's always about sort of what the program is exploring and how various disciplines and approaches can impact that. So subject matter expertise, providing sort of reviews of literature and things like that, and then some help with sort of program strategy. So, DARPA programs are all about how you manage them to function most efficiently and towards a specific goal. And so that requires a team of people, I think, to really kind of think through all the different ways with which that might happen.
Okay, so I think it was about a year and a half when you became a PM, a program manager. Most PMs end up managing just a few programs in their several positions, but I think you've got 7, perhaps even more than that. Some inherited from previous and other program managers, and some that you've pitched and were able to get approved through the harrowing vetting process here. So we can't talk about all these in depth, though I would really love to. Let's just talk about a few. And let's start with the Make It program, which I actually can tell you was started by a former program manager here, Tyler McQuaid, who I have a special fondness for because he was my first guest here on the Voices from DARPA podcast. So you've taken the baton
That's right.
to run the Make It program. So tell us a little bit about what the goal is and what the status is now.
The primary goal of the Make It program is to fully automate the synthesis of small molecules. And what I mean by that is we have a small molecule like ibuprofen that might be some sort of pain medication, or a small molecule energetic, or a small molecule agrochemical. Chemicals are sort of the building block materials for what we have on a daily basis, and we need to figure out how to make them. So by and large, right now, that's a by hand process. An expert chemist would go into a lab and mix things up in beakers and test tubes and round bottom flasks, and really define a route to a molecule. So that route is like a recipe that you might have in a kitchen to bake a cake with a certain texture and a certain flavor. And you don't know in advance what that route is, so you go in and you test out various steps to get to a particular molecule. So a molecule might take a 5-step synthetic route, which means I need to go from a set of starting materials and do 5 different experiments, or 5 different transformations, if you will, to get to the actual product molecule. That takes much longer than you might imagine in your head. To design a route to a molecule that no one's done before, it might take me 3 to 4 to 6 months to do. So what we're trying to do with Make It is actually provide computational tools that can help us define that route through machine learning, and then build a device that can actually implement that route for completely hands-free synthesis.
And I just need to stop you here with that machine learning as applied to chemical synthesis, which is very interesting sounding to me. I mean, it sounds like you have to gather a tremendous amount of sort of data from the chemical literature to feed to your machine so that it can pull out of that likely series of steps that would work to produce the molecule of interest. Did I get that right?
That's absolutely right. And there is existing data from the last 100 years of chemistry and what's in the literature. But we actually are having to generate a lot of that as well. Because as you might know, the data that you need to train machine learning algorithms is both what works, or the positive results, and you also need what doesn't work. And it turns out that scientists typically don't publish what doesn't work. We might have that captured in our lab notebooks, but we don't publish that information, and it's not available in databases.
And that's what you need so that your machine learning doesn't take you down a dead end, right?
So that's right. It needs to know what doesn't work, and we've actually had to both generate that computationally, so we generate sort of negative results, if you will, and we've also built a rapid screening platform that we can rapidly test various reactions, and we're collecting all of the data for the molecules that are made and then those molecules that aren't made, so those reactions that don't work. And we want all of that information to then feed into these machine learning algorithms to then help us understand what's the best path or recipe to get to a certain molecule.
Okay, so there's machine learning, but also in this, if I'm not mistaken, it's machine making, right? So this whole thing is really automated. Your machine learning is saying, try these 10 different synthetic routes, and then a bunch of gadgets are going ahead and doing it.
Right. So we're trying to accelerate both the brain of the chemist in terms of having to sort through and sift through what route to use and what route to test, and also then the implementation of that on a device, so that will be a fully automated process. And not only automated from the perspective of making one molecule, but we want one device that can make many molecules. And that's a pretty complex undertaking.
So as I envision the whole system, it's sort of making me think a little bit of sort of like a molecular version of the Star Trek replicator or something like that, but where maybe I would bring this make it gadgetry somewhere. I don't know, maybe to a battlefield where I might need this or that chemical. I mean, can you take us through an actual scenario? Let's say you're successful with Make It. You have these Make It technologies, these gadgets, boxes that you can ship somewhere. Who might want that, and what would they use it for?
I think about this in sort of two main ways. One is from the perspective of if there are times where you might need to generate some medicine, for example, remotely in the field. This device would allow you to do that. It would allow a non-expert to come up to the device and say, I want medicine X. And the device would then be able to define the route to that medicine. What is the most efficient route, most cost-effective route, the most environmentally friendly route, and be able to make that medicine for you. I also think about it from the perspective of reproducibility and enabling synthesis for fields, for a research tool, for fields that don't have synthetic expertise. So, for example, in the field of molecular biology, perhaps they could have a Make It device in their lab and generate small amounts of chemicals that they might need in their research without having to purchase sort of large products or products that aren't necessarily available commercially. They'd be able to then use this to enable their research as well.
Interesting. Okay. Well. Good luck with Make It. May you take it to the finish line. I want to now move to another program, which I find just absolutely fascinating: molecular informatics. We've all sort of gotten familiar with the idea of thinking of DNA, deoxyribonucleic acid, as an information-containing molecule. Contains genetic information. We often say it sort of has the genetic or the molecular information blueprint of a person. But you're taking this idea of molecular information to entirely different and rather audacious places. So can you talk about molecular informatics?
Yeah, sure. So molecular informatics is a kind of a crazy instantiation of really what would you do if you could actually store data in the physical form of a molecule. So nature does that, as you mentioned, in DNA. That's how we store information for our genetic codes. And there is work going on to store actual digital data, zeros and ones of our digital world in DNA. So DNA has these 4 building blocks, and you can essentially code the zeros and ones of our digital data into these 4 building blocks. But when we started to think about this in terms of how we could both accelerate ultra-dense data storage. So that's the benefit that molecules provide is from a density perspective. You can store much, much more data in a very small physical form. But also then... You
mean as compared to, say, the transistor-based
that's absolutely right.
storage on a chip?
Or magnetic
chip.
Memory, things like that, tape
okay.
memory, yeah.
Mm-hmm.
But then if you do that, there are sort of 2 threads here. One is that nature uses 4 building blocks, 4 molecules to store the complex instructions for life. But there are millions of molecules. And why limit ourselves to those 4? So we started to think about this from the perspective of if we could actually sort of address and access the richer palette of chemistry to store data, what could that then enable from either a density perspective or a computational perspective? And that's where we started to see this mix between storing data and archiving it, which is really good with DNA right now. You write the data onto a DNA strand and you put it in a refrigerator and archive it for later. But could you actually use that information in the molecular form? So could you compute on that molecule for some function? So computations are like, you might want to do an addition or a multiplication, or you might want to do a search of a large data set, so a large image set, do some sort of machine learning on that image set. And what molecules offer is not only the ability to store data in a very, very dense way, but also very highly parallel processing. And what I mean by that is, chemical reactions happen relatively quickly, and they happen essentially simultaneously. So if you have a beaker full of molecules, you'll have multiple reaction paths all happening at the same time, as opposed to the sort of serial processing or one right after the other processing that we might think about for today.
And then are there particular kinds of problems where this molecular computation would be better than the kind of conventional computers?
That's exactly what we're exploring. We have hypotheses about where that might be true. We have some approaches that are looking at things like similarity search for a very large set of images. So can I find all of the images that have a red shirt? And can I do that much, much faster than a conventional computer might be able to do it? We're looking at problems involving signal processing and optimization. So how can you optimize a response? How can you get sort of the best function from that response? And what we're really looking at is can molecules enable us to do things like that faster? And or can they enable us to do sort of a computation that a conventional computer that sits on your desktop would not be able to do?
I just want to drill in on one part of this to see if you can help me understand, say, how the result of a chemical reaction, say in this molecular computation, somehow corresponds to a red shirt in an image or a white shirt in the image. How does that molecule map to the object?
So that depends on how you encode the information. So I'll give you an example that's kind of easy to grasp. We'll go back to DNA for a minute. So DNA, again, has these 4 base pairs, and we put them together in a string. And that string, we can then, with that string and the code that we use for that string, whether it's ACTG or GCTA, whatever we design as the code for a red shirt, we can actually then synthesize those DNA strands, and an image that has a red shirt in it will have that red shirt code, for example. So if I have a string of 100 of these ATC and Gs, the code for that red shirt will be embedded within that. And we can actually search for that very quickly in a molecular way. And with DNA, we might do that with complementary strands. So if folks understand that DNA is a sort of a double-stranded process, we're working on the encoding and data storage side with single strands. So we can use that sort of base pairing phenomenon that nature uses in DNA to then how do we reach in to that sort of liquid stew of data and then only pluck out those strands that have that code for a red shirt.
That sounds absolutely amazing. One thing that I think would be interesting to maybe try to give listeners a sense of is just how dense the storage can be. I mean, sometimes you hear people talking about storing the entire contents of the Library of Congress in something the size of a sugar cube, like the Library of Congress has become an information unit. So when you talk about DNA as storage, I mean, how much, this might be difficult, but in DNA that could pack into a sugar cube, like how much would that store?
One of the best kind of images I can provide is if you took all of the data that had been generated in the history of time up until like 2015 or 2016. If you stored that in DNA, you could pack all of that into something the size of an SUV.
Absolutely astounding.
To sort of put an exclamation point on that, what we're trying to do in molecular informatics is provide sort of practical DNA storage solutions that we can compute on, as I mentioned, but then access that broader palette of molecules, which might provide even higher density levels.
Right. So in that case, biological evolution leads to DNA with these 4 building blocks, A, C, T, and G. But that doesn't mean we have to stop there. If our purpose is something else like data storage, you might have additional building blocks or ones that have different functions.
That's right. That's right. And it allows us a lot more flexibility in our designs. We think a lot at DARPA about not only developing and enabling capabilities, but thinking about the ultimate sort of scalability and implementation of those capabilities. And DSO really is looking at things that we might actually realize in 10, 20, 30 years, but we always have that in mind.
Right, DSO Defense Sciences Office.
That's right, yep.
Right. Mm-hmm. Okay, so let's just touch on 2 of your other programs just briefly. One of them, ACDC, that stands for Agnostic Compact Demilitarization of Chemical Agents, and that just sounds like a great idea.
Yeah, it's a wonderful and necessary thing, unfortunately. So the ACDC program is designed to make transportable devices that can destroy chemical warfare agents. So really where we're headed with this is actually building a device that is almost a conventional diesel engine. So if you imagine a diesel engine, and what we're going to be doing with this diesel engine is using the chemical warfare agent as a fuel. So just like as you would burn diesel fuel in an engine, we're burning chemical warfare agent and destroying it in the process. So we can produce energy from this engine, but we are also then destroying chemical warfare agent. And ultimately, what we're building is a prototype. It's a pickup truck with an engine in the front that in this pickup truck can drive to a site, run off of the chemical warfare agent, destroy chemical warfare agent, and then we can drive out.
Wow. That's it's like swords to plowshares type of thing. Okay, may you absolutely succeed in that. You've tested this a few times.
We've tested the engine concept, and right now we're developing, we're building the full system and developing the prototype.
Okay, and the last of your many programs that we'll talk about right now is SCOUT. This is because I mentioned it earlier in the intro. That stands for Spectral Combs from Ultraviolet to Terahertz. And we're not talking about here about combs that we use to make our hair look nice, right? This is something else.
That's right. This SCOUT is focused on developing compact sources for spectroscopy. And spectroscopy is essentially chemical measurements of various species. So if we want to know what species are present in the air that we're breathing, we might use spectroscopy to find out. And SCOUT was really designed to take a capability that had been developed at a single wavelength and expand it all the way from ultraviolet to terahertz, as you mentioned. And the reason that you want to do that is because molecules behave differently when they're sort of energized, if you will, with light in the UV regime than they do in the terahertz regime. And different systems respond differently. So UV is very good for interrogating biological systems, whereas terahertz might be really good for really complex mixtures like breath analysis. So people are very interested in using terahertz-based spectroscopy for those complex mixtures. And so SCOUT had sort of 2 threads. One is to develop the materials to miniaturize very sort of high-fidelity sources for spectroscopy across the UV to terahertz regime.
Light sources.
Light sources, that's right, to use for this sort of spectroscopic application. And the other was to actually demonstrate, let's say that we can build these things in the laboratory. What can we actually do with them then in the field? And what we've shown is that SCOUT offers the ability to do things much, much faster than conventional systems. So I can take a spectrum in a matter of milliseconds where it might have taken me minutes to do before. And that's very important when you have something that is a matter of whether or not you want to know that there's been a chemical attack, for example. You want to know as fast as possible, and you want to know exactly what that agent was. This kind of spectroscopic tool can tell you that. And also, we've been able to show that we can do this spectroscopy over large distances, so kilometer length distances, which is really important to monitor larger areas. This might have implications in the oil and gas industry for gas leaks, for example, also for air quality monitoring across a city. There are a number of different factors that you could think about. And these are all eye safe. So we don't have to worry about safety challenges. And we're really looking to find out how we might apply this spectroscopic method in a DoD and then outside DoD context.
Right, and you did just mention along the way, even breath analysis, that begins to sound like a biomedical application, because I know there has been research indicating that there can be really subtle signs in the sort of the chemistry of an exhalation that can be indicative of some kind of disease.
That's right, and really what you're getting in something like breath analysis or any other biological or complex system generally is you're getting a lot of chemical, a lot of signals that might change frequently or over time, and the concentrations might be very, very low. So developing a technique that can do both deal with the complexity of the number of different analytes, if you will, the number of different things in that sample, and also do it very quickly and distinguish them from each other is really important.
Okay, and then just finally on this, that word comb, I take it it's because if you were to look at the distribution of wavelengths and sort of represent each one of those as a line, then there's many lines that in a way look like the tines of a comb. That's
right. That's exactly right. So you get a light source that provides many wavelengths all at once, but they have a very fine spectral resolution, which is really important, again, for these sort of complex environments we're dealing with.
Okay, so we've kind of touched on 4 of your programs, and we'll have to leave the other ones for another time, although our listeners can always go to the DARPA website and find out more about those. So you've been a program manager for about 1.5 years, and that means that you probably only have a couple more years to go. That's typically the case. So I'm just wondering, if you imagine back to your time here at DARPA, but from a vantage of 10 years from now, and you've examined what has come of your work, of your programs, say of Scout or Make It, what do you hope you will be able to say at that time?
Wow. I really, looking back, we spend a lot of time here, and I'm spending a lot of time thinking about where might these things go? And that's a lot of what DARPA does, is build relationships with other organizations to transition the technologies that we develop. And so I already see seeds to what that answer might be. There are some projects I have where it's going to be continued scientific and technical development. There's going to be a lot of knowledge generated out of them, and it might be 20 to 30 years before anybody sees anything, and it might not look anything like it does today. I think for a program like Make It, we might actually see these systems, and we might actually see some generation of the systems that we're building now as a first generation as commercial devices. We might see some seeds of industry and sort of the chemical production industry using some of the computational tools that we're developing. I think programs like Make It and ACDC, I can see a very practical sort of fielded application. And more programs like molecular informatics, I think we're just at the forefront of defining what are the questions we should be asking to really begin to understand the opportunity for molecules in something like computing.
Right, and as I game this out myself, if I try to be you for a minute, I mean, if I knew, say, 10 years from now, that the AC/DC technology that I worked on helped to decontaminate tons and tons and tons of very dangerous chemical warfare agents, wow. I mean, I would feel like I have accomplished something in my life. I
have to say, even being at DARPA on a daily basis is a humbling experience. But then, seeing something that you're working on and that your performers are working really hard to develop become used in either the DoD or a broader context will be incredible.
All right, and then as we're getting toward the end here, but I did just want to touch back on an interest of yours that you expressed way back when you were a graduate student, and when you were a woman entering the world of science and in what traditionally has been a male-dominated kind of world. But going further, not just getting through that yourself, but also trying to inspire younger women and girls to do the same. So the Girl Scout interest patch in chemistry. I want you to say a little bit about that particular experience, and then if you've actually continued that kind of interest even later in your career.
Yeah, so that interest really started in college and graduate school. I was actually part and held leadership roles in organizations at both my undergraduate and graduate institutions. That were really geared towards sort of women scientists. And we did outreach to young girls and worked at science fairs and things like that. But we also then were a community for each other and the faculty at our institutions. It wasn't something limited to a student population. It sort of crosses all sort of professional levels. And I learned a lot through a lot of those conversations about explicit bias and implicit bias and all sorts of quote unquote reasons, that there is an underrepresentation of both women and other underrepresented groups. But for me, it wasn't about finding the answer or the reason. It was about sort of empowering those around me. And that happened at that level. It still happens today, but I think I do it a little bit more organically now as opposed to being involved in organizations. It's much more about mentoring and trying to fill a hole that other women might have in terms of, having a circle of people around them, men and women, to help mentor them and grow their careers. And that's one thing that I do try to focus on. And also then, again, make sure that I have that in my own life as well, because it's important for everyone actually to make sure that they build those relationships for folks to help them teach and learn and grow.
Okay, so we're actually out of time, but I just want to ask you if there's anything about science, DARPA, your career as a chemist, or anything else that just didn't come up that would be of interest, do you think, to listeners?
Well, you didn't ask me how fun this was.
Well, tell me, how fun is it?
Well, this being the podcast, but also life in general at DARPA. And I say that because we get to interact with amazing, top-notch scientists on a daily basis, multiple times a day. And that's really exciting, and it's really fun, and it's an amazing opportunity. And those are the folks that are doing the hard work to implement all of the ideas that we might generate here, really put them to practice. And again, from the perspective of coming to work every day and being humbled by that, and being so excited and energized by what they have to bring in terms of their ideas and their talents.
So I just want to thank you for spending time with me in the studio and getting me up to speed on your programs.
Thanks. This was fun.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about Ann Fisher, the programs she and her colleagues run in the Defense Sciences Office, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.